We've got a lot of terminology in this title. Actually, some of these are new to the CySA Plus exam, as well as for the entire cybersecurity domain. Now, a few years back, you couldn't find anything related to containers or microservices in data centers or cloud environments, and now they're everywhere. And if it's a new technology, and if it's growing rapidly, it's probably awesome. But how do we secure it? Now, before we dive into all these things in the title, let's just get one thing straight. Virtualization, virtual machine. I really hope you're not studying cybersecurity without knowing what's a virtual machine. Anyway, just to be sure, virtualization means the ability of running multiple operating system instances on top of a single hardware computer. Now, this is made possible by running just a single piece of software on top of the hardware, which is called the hypervisor. And this hypervisor is responsible for creating, launching, managing resources, and maintaining all the operating system running on top of it. Now, some people would say from a security perspective that VMs are more secure than physical servers, simply because they are located by default behind an additional layer, the hypervisor. So that's one more step to overcome when attempting to compromise a VM, kind of like a defense in depth without intent. And they can be more secure also because the hypervisor provides much better visibility into what's happening behind the scenes. Now, how your VMs are behaving, how many resources they're using, and so on. But don't forget two ideas here. That the hypervisor is also an additional piece of software in itself that can be attacked and exploited. Just like any other software, it's basically a minimal operating system that can be exploited, and that any virtual infrastructure will have some management software in the back end that controls the entire virtual environment. So unauthorized access to that management interface, to that management console, thinking about something like vCenter, for example, for VMware, means that all your virtual systems can be compromised. So take this security discussion with a grain of salt. All right, so let's talk about VDI, right? A more specific type of virtualization is VDI, that's virtual desktop infrastructure. The main idea behind VDI is to use virtual machines instead of physical machines or desktops or laptops to provide workstations to our employees. Now, since the user cannot really work with an empty desk, VDI is going to use something called a thin client, or a thick client, or it depends on the terminology. Anyway, it's going to be a minimal computer with a small operating system, a screen, a keyboard, a mouse, some peripherals in there, some USB ports, and the network connection to your data center. Now, when the VDI client starts, it doesn't do much, but it initiates a kind of a remote desktop connection to its corresponding virtual machine in your data center. Now, VDI is great from a management perspective. It's extremely easy to deploy new desktops, to repair, to rebuild, to apply security policies. If a user gets infected with malware, you can simply restore its desktop from a base image in a matter of seconds, or a minute or two perhaps. Not to mention that the user gets the same experience and the same files, the same desktop, the same environment, same resources, regardless of the user's location or even regardless of the device that he or she are using. I mean, they can even connect from a smartphone to the same desktop. And it all sounds great from a marketing perspective, right? But with VDI, be careful with backups and redundancy, because all the workers now depend on one single infrastructure. An issue in the VDI data center leaves your employees without all their desktops. And I'm not just talking about a fire or a flood in the data center, but just a misconfigured policy that locks everyone out and nobody's able to authenticate, or a misconfigured firewall policy that blocks everyone else's traffic to the data center. Now, any issue with this is going to bring down productivity all over the place, right? So basically you'll need to send everyone home because they won't even have Notepad to work with, or at least not the digital version of Notepad. So it's a single point of failure. Your data center and the connection to your data center becomes a single point of failure. Of course, the cloud is a great environment for VDI because we already have everything virtualized in there. Also, we have solutions from Citrix, from VMware, from Microsoft, just a few of the many vendors out there providing cloud-based and cloud-managed virtual desktop environments. Just to give you some starting points, Here's the partnership between Citrix and Google for virtual desktop environments. There's also a partnership between VMware and Microsoft for running Horizon Cloud on Microsoft Azure, or you can even use the built-in solution readily available from Microsoft Azure for virtual desktops. Another concept here that's worth mentioning is SOA, that's service-oriented architecture, and the story goes like this. Now, traditionally, designing an architecture based on a computer network was all about choosing the right devices or boxes with their specific functions and deciding where to place them within the network. Now, with virtualization, the issue of placing those boxes has become highly flexible, which leads to a business-focused design. So we can think about the business first and then design the network or the applications in such a way to match the business requirements, right? And then we reconfigure them whenever those requirements change. We live in such an interesting world. So SOA relates to this concept by introducing the design of virtual services closely mapped to business workflows. Now, in order to accomplish this, each service must have well-defined inputs and outputs, and it can be regarded as some sort of a black box with a simple interface. They can be composed of other sub-services, so we have this type of flexibility. They must not rely on any kind of external state, and this decoupling of services means that we can upgrade them completely independently. And of course, we can even code them independently. We can use any programming language as long as they're still compatible with the interconnecting services and they can talk to each other. There is a much simplified interoperability between the services compared to the monolithic applications where we had all the code in one big piece of code, one big block of application where all the functionality was built in, was baked in, because services have much simpler interfaces. And of course, we need to ensure that these services can communicate to one another, right? And they can be interconnected using an abstracted communication method called a mesh, or sometimes called an ESB, that is an enterprise service bus. And we do have to mention containers as well. Now, containers are some sort of a weird animal here. Some would say that they are the next technological iteration after virtual machines, which is why they're referred as user space virtualization sometimes. Now, containers don't run on top of a hypervisor and don't even run operating system instances. Instead, containers are just isolated environments dedicated to running a single application built on top of a single operating system and managed by something called a container engine. Now, these isolated environments can have their own resources allocated to them, their own file systems, they can see their own processes. So any application that runs in such an isolated environment that is a container thinks that is the only application running on a dedicated system. So we have a type of isolation between containers very similar, or we try to make it very similar to what we had with virtual machines, except that we don't need to boot up a separate operating system for each environment. All the containers on a host are all going to be using the same operating system, the same kernel that is installed on that host. Now, having the operating system overhead removed, now containers can be extremely fast. Actually, a new container can be created in just a few milliseconds, adding some time for the application that runs inside of that container to start as well, and just as easily destroyed or recreated. And of course, the most popular technology out there is Docker right now, but it's definitely not the only one. And the flexibility makes containers useful for things like development. Now, we have developers instantly creating and destroying test environments to test a new piece of code, to perform even a unit test for a minor change, and also allows developers to quickly switch between environments and test different types of environments with the same code. It's also very good for packaging and distribution because it makes it so easy to ship applications, to download, to make them available for download for the customers, and to run them as container images. You don't need to worry about dependencies and how the application is supposed to be installed anymore because the container already has everything in it. Batteries included, as Docker says, right? It has the application and all the necessary dependencies in one single place. So you get a break from all that dependency hell that you're used to managing when running multiple applications with different dependency and library requirements on the same machine. Now, each and every application is isolated in its own environment right next to its exact and perfectly matched library requirements. Containers also come with additional technologies for storage, for managing networking, for managing security. Of course, everything is virtual, so the storage is abstracted in software. The networking is actually software-defined networking, as you can probably expect. And one more benefit here, for example, Docker also lets you describe the infrastructure as code. Now, you have Docker files that describe the build process that is executed, is performed in order to build container images. We also have Docker Compose files that describe environments, entire environments, like the containers, the networking that binds those containers, the storage that attaches to those containers, everything that you need in one single file of code. And of course, we need to talk about security here. And the absence of a hypervisor does not immediately mean that containers are not as secure as VMs. But in my personal opinion, they are not as secure out of the box, which means that you have to take some additional precautions to keep containers secure, or to make them as secure, at least, as virtual machines. Out of the box, containers are pretty permissive. Also, keep in mind that containers are running on top of a full Linux or Windows operating system, which can have lots of weaknesses and an increased attack surface, at least in comparison with a minimal hypervisor. So make sure you read a patch and validate from a security perspective the operating system that's running on a containerized host, because compromising that operating system means compromising all the applications that are running as containers on that single host. And we've closely touched on the subject of microservices by talking about containers. And we already said that SOA, service-oriented architectures, allows us to map an IT architecture to business processes. Now, microservices are very similar to the SOA approach because they also involve splitting larger functionality in a bunch of smaller interacting subservices. But the reason that we're doing this is because it's easier to combine these microservices. We don't need to know how they work. We just need to know that they do one job and they do it very well. We can consider these microservices as black boxes, self-contained, but with very clearly defined inputs and outputs. And of course, just like in SOA, we can replace, we can upgrade, we can change any component individually without affecting the entire application as a whole, even from different vendors. What we do need to make sure that it happens is that microservices can communicate to each other properly. And as you can see, microservices are really similar to the SOA approach, and in fact they are, but SOA is focused on mapping business workflows to those IT systems that we talked about that support them and allows a service to be built from other sub-services, while microservices bring the same concept to software development and do not allow any sub-services to be defined. That's also why they're called microservices. There's no smaller functional component smaller than a microservice. And the concepts behind microservices also closely relate to, first of all, agile development, and secondly, to the Unix-based philosophy, which you might have heard about. That is, that each piece of software should do just one single thing and should do it extremely well. And the good news is that cloud environments are extremely friendly with this approach, and regardless of where they are implemented, containers are the #1 solution for a pure microservices-oriented architecture. Now, SOAP has to receive a special mention here simply because it has been around for so long. Remember when we mentioned that those services in the service-oriented architecture can be written in any language as long as they can properly interact with each other? Well, this compatibility was for a long time ensured by SOAP, that is, Simple Object Access Protocol. Now, SOAP manages this business of sending and receiving messages between application components in SOA using XML messages, and along with its complexity, it is a very high overhead protocol. And SOAP is not just complex for the sake of being complex, but it also has some welcomed built-in features, also called security extensions. So it implements authentication, it supports encryption, it can support asynchronous communication, and advanced error handling. And because SOA and SOAP create new communication pathways between services, we are facing new risks as well. We're increasing the attack surface. First of all, we have risk of probing. This is similar to a scan or a brute force attempt. Probing allows an attacker to discover the various requests accepted by a web service and even view all its functions. So it's basically scanning web services. And of course, since we're talking about inputs, any unvalidated input can lead to data disclosure, privilege escalation, or simple crashes. We also have coercive parsing. Now that's a mouthful. Basically, this relies on the fact that the web service will attempt to internally process any XML request that we send to it. Again, input validation, at least to figure out if it's a valid one. Excessively large payloads, or the so-called XML bombs, can act as a denial of service for the web service itself. Don't forget about external references. Again, a type of attack facilitated by some improper XML validation, which might lead to either a denial of service or data disclosure. Malware, simple malware, the traditional problem of unvalidated input that might include executable code, performing buffer overflows, executing malicious code, privilege escalation, and so on. SQL injection, even SQL injection, knowing that some XML input to a web service is used in SQL queries later on, can expose the application to the same risks as a non-sanitized input field on a web page where SQL injection could be possible. But nowadays we have something modern instead of that SOA approach and those XML messages. And we call this method REST APIs. I'm sure you've heard about them. So finally, APIs are a very popular way to interact with systems, with applications, with services, with web services. And they are used in scenarios such as interacting with web services in a programmatic way, like from scripts or tools, automated tools, orchestration tools, including programmatically creating and managing resources in cloud environments. Also, they're used to enable machine-to-machine communication or web services communicating to each other. Now, initially, the standard was SOAP, which was based on XML. Now we have REST APIs, which use HTTP, hopefully HTTPS, and REST stands for Representational State Transfer, which in essence, it's a much simpler implementation and specification compared to SOAP. Now, from a security perspective, you should know about APIs because they're definitely a solid attack surface. They are a gateway into your applications, your services, and depending on your level of virtualization, they might even be a doorway into your infrastructure as well. We are using API keys to interact with the services, to interact with the infrastructure, which work as a secret key used for authentication, so we should make them secure. And since nowadays you'll probably see REST APIs everywhere and they use HTTP, do the world a favor, and I know I'm repeating myself here, make sure you actually use HTTPS everywhere. So in REST, each resource should be accessible by a distinct URL, which can be accessed using HTTP verbs, GET requests, POST requests, and so on, instead of XML documents, like in SOAP. So for example, in an online shop, let's say, an URL that ends with /electronics might point to a collection of all the electronic products on the website, while a URL that ends with /electronics/ a specific ID would point to a specific unique product by its numerical ID. And REST responses that we receive from the API endpoint can be in any format, depending on how the API has been configured. Most of the time, you can even choose the format of the data to be returned back to you. Most of the time, it's going to be JSON, but they can also be XML or CSV or any type of implemented output format. And just to wrap things up here, we also have some principles that define how REST APIs should be designed. First of all, we have the requirement that all the requests should look the same, so we need uniformity, and resources should be uniquely identified using a unique URL. Secondly, we need a decoupling between the client and the server. They must be completely decoupled, and the REST API should be the only means of communication between those two entities, between the client and the server, so no back channels in there. They shouldn't store any state information. That's where the state transfer comes from in REST. That is, each request must encapsulate all the information required for processing, including any kind of state information that might be relevant. So there shouldn't be any server-side sessions, at least not as part of the REST API design. This is supposed to help with both performance and scalability on both the server and client side, basically making both their jobs easier. And finally, information should be cacheable when possible, again, for the same reasons of improving performance and response time. So that's it for today. A lot of terminology here, but make sure you can explain and you understand for yourselves how containers work. What's a service-oriented architecture? What's VDI? What's the difference between a virtual machine and a container, and so on, right? So remember all the things that we talked about because they will be useful on the exam day, right? So thank you so much for watching. If you like this, like the video and subscribe, and see you next time when we're going to be talking about infrastructure as code, CI/CD, and DevOps. So good luck and see you next time.